Couple of things to review for our complex number assessment or post-assessment. So first one is product property when it comes to radicals, and then also specifically when it comes to complex numbers, like when there's a negative number inside the radical. So first we're going to start with what it kind of looks like with positive numbers. So if I have, say, the square root of 16 times the square root of 4. The product property says that, if I multiply these two separately, like the two square roots, I should get the same thing as if I were to like multiply the numbers together inside the radical. So we'll just kind of test that out. So if I go ahead and multiply the two numbers inside the radical, 16 times 4, and then I'm going to simplify the left side of the equal sign a little bit. So like the square root of 16, that is 4, times the square root of 4, that is 2. And then over here, the square root of 16 times 4, I can go ahead and multiply those. That's 64. And then if I multiply 4 times 2, that is 8. And if I multiply 64, or not multiply, but if I take the square root of 64, that is 8 also. So it just kind of proves how that property works. We just want to check to see if it actually works when there's like negative numbers inside the radical as well. So let's say I'm just going to go ahead and take like the same exact numbers but make them negative in this case. So I'm going to take the square root of negative 16 times the square root of negative 4. And then I'll go ahead and multiply them together inside the radical as well. So negative 16 times negative 4. And then simplify it like kind of in the same order as when they're positive. So for the square root of negative 16, that's 4i. And then for the square root of negative 4, that's 2i. And then for the square root of negative 16 times negative 4, if I multiply negative 16 times negative 4, that is 64, positive 64. And then if I multiply 4i and 2i, well, if I multiply 4 times 2 is 8, and then I times I is I squared. And then over here, the square root of 64 is 8, but we know that I squared is actually the same thing as negative 1. So whenever we see an I squared inside of an equation or expression, we should replace it with negative 1. So this would technically become 8 times negative 1 right here. And then this 8 stays the same. We already finished simplifying that. So 8 times negative 1 is negative 8, and then that doesn't equal 8. So because they kind of get different signs, it proves that the product property does not work for complex numbers. So when we have a negative inside the radical, we can't extend that same property. It's very, very similar, but it's not exactly the same. And then the next section is simplifying powers of I. So before we get into the actual little practice problems, I want to draw the table for us. So I to the first power, of course, just simplifies to I. I squared is negative 1. I to the third power is negative I. And then I to the fourth power simplifies to a positive 1. Okay, so this table starts to repeat itself like every fourth one. So like the next one would be I to the fifth, and it would simplify the same thing as I to the first power. So it just kind of starts to repeat itself. So because it starts to repeat itself, we can use that pattern to simplify higher powers of I. So for example, if I had I to the, say, 31st power, if you want to figure out what this would simplify to, you take the exponent, so we would take 31, you divide it by 4, and you're always dividing it by 4, and that's because the table starts to repeat itself every fourth round basically. So it's always divided by 4. So 31 divided by 4, obviously it doesn't go in evenly, but we can do 31 divided by 4, which would be 7, with a remainder of 3. Because 7 and 4 would be 28, and then plus 3 to get to 31. So that remainder tells you what part of the table to look at. So whatever the remainder is what power you like kind of line it up with on the table. And then that's what it simplifies to. So because it simplifies the same way as I to the third power, it would become negative I. Okay, and then I'll do a couple more really quick. Now we got it. So let's say I take I to the 50th power. Same approach. So we take just the exponent, the 50, and then we would divide it by 4. Notice I'm dividing by the same thing. Still divided by 4. It'll always be by 4 for these problems. And then 50 divided by 4 is 12 with 2 left over. So 12 with a remainder of 2. And then from there, we take our remainder and we line it up with the table. So remainder is 2, so we look at the I squared column on the table. And I squared simplifies to -1, so does I to the 50th power. So -1. The only thing you have to be a little bit careful about is let's say I had, do one more. If I had I to the 36th power and I were to take 36 and divide it by 4, so 36 divided by 4. 36 divided by 4 is 9 with no remainder. So if there's no remainder, that means it's an exact multiple of 4. So it lines up with the I to the 4th power on the table. So that means that this would simplify to +1. Okay, and then the last two last section, last problems, is just comparing real versus imaginary expressions once they're simplified. So both of these examples are ones where we would FOIL them, so we'll go ahead and FOIL. So 3i times 3, you just multiply the 3s, so it'd become 9i. 3i times -5i, so we do 3 times -5 is -15. And then I times I would become I squared. And then 5 times 3, so plus 15 right here. And then 5 times -5i, so 5 times -5i, we would just multiply the 5, so 5 times -5 is -25. And then the I just tags along. And we want to combine like terms if we have them, and then just kind of simplify each part. So 9i and -25i, we can definitely combine those. I'm also going to go ahead and replace this I squared with a -1, because anytime you have a higher power of I, you need to simplify it. So I'm going to do, I'll probably combine my 9i and -25i last. So I'll start with -15. Replace my I squared with -1, and then bring down the plus 15, and then I can combine 9i, -25i, those together are -16i. And then from there, I can just go ahead and multiply -15 times -1, which is a +15, plus 15, minus 16i, and then I can go ahead and just add the 15s together. So 15 plus 15 is 30 minus 16i. And then this would be considered an imaginary expression because, or a complex, expression, because it has I in its answer. So this would be considered complex. And then for the second one, same approach. We're still gonna multiply it, FOIL it. So 10i times 10i, you do 10 times 10, which is 100, and then I times I, which is I squared. 10i times 3, so that would be 30i. -3 times 10i, so -3 times 10i would be -30i. And then -3 times -3 times a +3, that would be a -9. And then I can simplify, combine like terms. So the first thing I can do is replace that I squared with a -1. So 100 times -1. And then I have some like terms. I can combine the 30i and the -30i. Since they're the same number and opposite signs, they actually just cancel each other out. So I can bring down my -9 from there. And then 100 times negative 1 is negative 100, minus 9, negative 100 minus 9 is negative 109. But you see, like in our final simplified answer, there's no I anywhere. So this would not necessarily be considered complex. We could say it's a real number, it's a real solution, not solution, but real answer.